right, welcome back. Hope your weekend went well and that you enjoyed your extra hour of sleep, which, because time is conserved, at least on the time scale that we live at, you will have to give back in the spring. I don't know why we do this to ourselves. All right, we were talking last time about kinetic isotope effects, particularly secondary kinetic isotope effects, which relate to rehybridization of an at the rehybridization of an atom that you're substituting hydrogen versus deuterium at in the transition state of the rate determining step. So I want to give you an example of a situation where this can be useful in trying to understand reaction mechanism. So this example comes from biology, and it involves the cofactor Fad, which is an oxidizing agent. It's kind of like NAD+. It's got a different reduction potential. But like NAD+, it's an electron acceptor. And this is its structure. Do you need to memorize this structure? No. And what this reaction involves the reduction of an amino acid, which I'm just going to draw like this and not worry about the stereo center. But this reaction will reduce the amino acid, oxidize the amino acid to an amino acid right. And then the other thing you get is the reduced form of FAD, which is FADH2, and it has a couple of hydrogens in places that it didn't before. Again, is this anything you need to know or memorize? Not particularly. That's meant to be a six-membered ring, but I'm embarrassed at it, so let's try again. Okay, close enough. And so there's a couple of different mechanisms you could propose for this reaction. Both reaction mechanisms that you might propose would involve a base removing the alpha proton from the amino acid to get the corresponding enolate. Oops. Which would be resonance stabilized. And let's sort of look at that structure. Negative charge here. Probably at this atom. What do you think the hybridization is there? Probably sp2, right? Why is that? Right, the lone pair needs to be in resonance with the carboxylate group, delocalize it. And so, yeah, you expect roughly sp2 hybridization here. Then, in the next step, so once you get to this conjugate base, there's a couple of different possibilities, okay? And for our purposes here, we need to assume that this is a fast equilibrium. So option A is for this amino acid to attack FAD plus in basically conjugate addition kind of format. So I'm sorry that we're drawing this horrible thing multiple times. It's good for you. just like eating your peas. All right, so notice in the FAD structure, you basically have an extended conjugated system here. It's almost like an alpha-beta unsaturated carbonyl compound, only it's alpha-beta and gamma-delta unsaturated. In any case, one option is to have the enolate attack here, and we'll move electrons there, and we'll get the following intermediate. And we'll just stop there for this particular, oh man, I think my drawing skills have gone down a little bit. Okay, so this is an intermediate, and notice that at the carbon that used to be sp2 hybridized, we're now probably sp3 hybridized. And of course, this would go on through another couple of steps to give you the amino acid. And the rest of that reaction mechanism isn't that hard, but it's also not really important to our discussion today, so we'll go ahead and ignore it. And then a second pathway, so this was pathway A, a second pathway B involves something really weird, and that is for, and this is kind of hard to draw a mechanism of, but this involves single electron transfer from the amino acid to FAD. And how does that happen, and why does it happen? I don't know. Presumably the reduction potential of FAD is such that you could add a single electron to it. So what would that look like? Well, that's kind of hard to draw, except after the fact the alpha carbon on your amino acid is going to be neutral. And then you somehow have to draw the FAD radical anion, which it doesn't totally matter how you draw it. The molecule just needs one extra electron. One way that you could consider drawing it might be to have a lone pair here and a single electron there, and then a negative charge here. All right, this is the FAD radical anion. Okay, and presumably this single electron transfer step is slow. Okay, so whereas for pathway A, it's the direct attack that is the slow step. So notice in pathway A, there's a hybridization change in the slow step from sp2 to sp3, whereas in the single electron transfer step, before the reaction, you're roughly sp2 hybridized, and after the reaction, what do you think hybridization is there of that radical? You got to think back a long time ago to when we talked about geometry and Q-mot and radicals. They invert quickly, but on average, you can think of them as sp2 hybridized. Okay? So basically, not much of a hybridization change here in the rate determining step. And the next steps aren't important. You could get to this intermediate in a subsequent fast step simply by doing the radical reaction between the Fad radical anion and then the radical amino acid. And then the subsequent steps would be the same. So how do you tease out these two mechanisms? Well, in one of them, the slow step has hybridization change. In the other, the slow step has no hybridization change. So when we go from sp2 to sp3 in the rate determining step, and there's a substantial amount of rehybridization from sp2 to sp3 in the transition state, you would expect, if you could swap out hydrogen versus deuterium, you would expect a kinetic isotope effect, a secondary kinetic isotope effect, and if you measured it for the direction going from sp2, which is a less stiff force constant, to sp3, which is a more stiff force constant, you'd actually expect an inverse kinetic isotope effect. You'd expect the rate constant for proton versus deuterium at this carbon, if you could do it, would be less than 1. Whereas for the single electron transport step, hybridization doesn't change. So you probably expect no kinetic isotope effect. Okay? And they did the experiment. It turns out this particular amino acid substrate was inconvenient. They used something else that looks like an amino acid enolate. The particular identity is not important, and why it worked isn't important, but they gave the enzyme the following two substrates. Oops. And they must have known that something like this could work. Notice that this portion of the molecule mimics the carboxylic acid, and then in place of the amino group you have a methyl group, and in place of the R group you have a hydrogen versus deuterium. But what they observed when they did this experiment for the rates is they observed the following kinetic isotope effect, which supports pathway A and indicates that, at least for this reaction, it's probably not single electron transfer. So anytime you're sitting in a biochem class and they show you a mechanism, if it's, in many cases, it will have been teased out using experiments of this nature. Sometimes in organic chemistry, you'll be asked, draw a reasonable arrow-pushing mechanism for this reaction. And if you don't have kinetic data, then maybe you could find a couple of different ways to do it. And so kinetic data are really important in being able to figure out what's going on in a transition state and discerning between various possibilities. All right, that looks kind of messy. I'm sorry. Any questions you want to ask about that? Okay. So the next thing we need to talk about is kind of fun. And it's fun because it's somewhat easy to understand. It's related to electrophilic aromatic substitution reactions and substituent effects. But this is a method for trying to tell, does the transition state of the rate determining step have a buildup of charge? And it can actually be positive or negative. All right. So another way to talk about these substituent effects is what are called linear free energy relationships. I don't think we'll talk in detail about what that means, other than to say that a linear free energy relationship is where delta G or change in activation energy for a molecule with a proton versus a molecule with some other substituent is related to a parameter, is linearly related to a parameter that describes how good X is as an electron donor, or in some cases, or a withdrawer relative to hydrogen. And the classic example is the Hammett linear free energy relationship. And so people will talk about a Hammett parameter, sigma, and this is derived from the following reference reaction. So at some point in the past, people actually did these experiments and defined these parameters sigma. So the experiment was deprotonation of benzoic acid derivatives. So what's a benzoic acid? A benzoic acid is where you have the carboxylic acid directly attached to the benzene ring, and then you would have a substituent here, which we'll use as X, okay? And you would simply measure the position of the equilibrium here for the ability of that benzoic acid to protonate water to give you H3O+. Okay, so simple acid-base equilibrium. Basically, we're measuring pKa's of benzoic acids. All right, and then you're going to take the log of the equilibrium constant for whatever X is, and then you'll use the equilibrium constant for when X equals hydrogen. All right, so you would be comparing the following two equilibria. Whoops. One where X is some substituent, and another where it's just a proton, just regular benzoic acid. All right, so let's make some predictions based on what you know. And for any given substituent, this ratio between the equilibrium constants and then taking the natural log is the Hammett parameter sigma of that particular substituent. Why do we take the log here? Well, do you remember that free energy is related logarithmically to the equilibrium constant? And ultimately, we're going to be using these Hammett parameters to try to understand things about free energy changes in reactions or activation energy. So that's why we take the log. All right. Another reason we take the log is sometimes these numbers can vary over multiple orders of magnitude, and we get sick of writing in scientific notation because we are lazy. If we wanted to write often in scientific notation, we would have been physicists, but we're not. So there we go. So let's talk about what we might predict. Do you think it should be easier or harder to deprotonate benzoic acid if you had methoxy here instead of hydrogen? What do you think? So what's the argument for difficult and what's the argument for easier?
If it's a methoxy group, then it's an electron donating group, so it's the electron density around carbonyl part increases basically, which is going to hold the hydrogen close.
So you're saying methoxy is an electron donating group by resonance?
Yes.
Meaning that if I were to draw this, I could also draw a resonant structure. what a horrible, horrible six-membered ring. Goodness. Okay, then we're just about to draw a Texas carbon, so that's embarrassing too. Okay, so that's a valid resonance structure, and what does that have to do with acidity?
So if you have that as an electron donating group, it should stabilize the carbonyl center there.
Okay.
So, if that is deprotonated, the stability of that carbocation intermediate will make a stable base. So I think having that as an electron donating group will rather make the deprotonation easier.
Okay, so let's talk about that. The conjugate, we often rationalize stability by looking at the stability. We rationalize acidity always by looking at the stability of the conjugate base. The conjugate base has a negative charge in this carbonyl. If methoxy is an electron donating group and can put extra electron density into the benzene ring that is adjacent to the negative charge in the carboxylic acid, that would be destabilizing, right? You're pumping negative charge towards something that's already negative charged. So you'd expect that to be destabilizing to the conjugate base. Now, your expectations might be attenuated by the fact that methoxy is an electron withdrawing group by an inductive effect. That is, oxygen's electronegative, and so through the sigma bonds, it can pull electron density away from the ring. So you might you'd need to offset those two things in your consideration. But we can look at the numbers. When X equals methoxy, this sigma parameter which is the logarithm of the equilibrium constant for methoxy at the para position versus hydrogen, actually equals minus 0.27. What does that mean? Is the reaction, does the equilibrium favor products more for methoxy or for hydrogen? Let me try that again. This is a ratio, and the log of that ratio is negative. Which is the bigger number, numerator or denominator? I'm assuming you know how logs work. Okay.
And it's been years.
Fair enough. And it's been years.
Just doing logs.
Okay. I had to just that's fine. And I had to. You've never had a frustrating experience until never mind. You've had plenty of frustrating experiences. But what's also frustrating is when a teenager comes to you for help with math. And first of all, it's been so long that you're not sure you can actually help them with the math, but then as you do try to help them, they get angry at you. I had to try to do logarithms with a child. The log basically asks, and the log can have any particular base, but let's talk about the base 10 logarithm of a number. The log asks, what exponent do I have to raise 10 to get that particular number? So the log, base 10 log of 1 is 0 because 10 to the 0 equals 1. The base 10 log of 100 is what? 10 to the what equals 100? 2, right? So the base 10 log of 100 is 2. So this question, what do I have to what power do I have to raise this ratio in order for, so that 10 to that number equals this ratio? That's minus 2.7. What is that? What do negative values for the
hydrogen is bigger.
Right, because logs go negative when you have a number between 0 and 1, right? The base 10 log of 1 over 10 equals negative 1 because 10 to the negative 1 equals 0.1 equals 1 over 10, and so on. So the fact that this is negative means that the equilibrium constant for hydrogen is bigger than the equilibrium constant for the methoxy group, which is consistent with what we said and what we expected, because you think the methoxy group's going to destabilize the conjugate base, so benzoic acid should be more acidic than the methoxybenzoic acid. All right? But in reality, we don't care that much about benzoic acid deprotonations and equilibrium constants, but we're going to use this number to describe how good of an electron donating group is methoxy. Okay, and that's going to be our reference reaction. Because we're saying, since we understand this deprotonation reaction, we expect good electron donating groups to make the equilibrium less favorable. So if we were to test other substituents and they had similarly negative values, we could say, oh, this group is similarly good at donating electron density as is methoxy. You follow that reasoning? A little bit? Okay. So let me give you some examples, and this is where you're going to start to get, things are going to start to sound familiar, because we're going to run through the same list of substituents that you did with electrophilic aromatic substitution. I'm going to say that these sigma values are for para substituents. And we can talk about why you'd expect the numbers to be different for para versus meta substituents. But at this point, I'm just going to indicate para here so that we know where X was. I already told you that for the substituent of methoxy, our number was negative 0.27. For the amino group, so having the para-amino benzoic acid, that number is even more negative. Okay. Let's go back to what sigma means. That means relative to that the equilibrium constant here for amino is even smaller than the equilibrium constant for methoxy. Okay. Meaning the para-amino benzoic acid is even less acidic than the para-methoxy. Any reason for why that should be? The amino group is a better electron donating group than methoxy. Why is that? It's true. Why is that? Yeah, go ahead, Joshua.
If you view it as an sp2 and H2, which isn't 100% true, if you view it that way, you have an FDP, full P orbital.
Okay.
Then donate directly into the electrolyzer.
Okay. So the lone pair on the nitrogen can donate into the aromatic ring if it's conjugated, and if in particular if it adopts sp2 hybridization, which it will, to take advantage of conjugation. But presumably methoxy has a lone pair that you could put in a p-rich orbital and conjugate to the ring. So what's the difference, nitrogen versus oxygen, that would explain this? Sorry? Electronegativity, right? Which literally means that the electrons on oxygen are lower in energy than the electrons on nitrogen, so nitrogen ought to be a better donor, okay? So we're learning obvious things here, but we're putting numbers on them. And we're going to use those numbers to try to probe other reactions. So you could run down the list of things. If you do hydroxy instead of methoxy, you get a number that's in between the amino group. Should you memorize all these numbers? No, but it's just the usual suspects here in terms of what you've learned for ranking electron donating groups versus withdrawing groups. In fact, the trends that are in the table in that undergrad textbook probably come from an analysis like this. If they don't come directly from evaluating the rate of electrophilic aromatic substitution, they would certainly come from this reaction. Notice that you expect alkyl groups to be electron donating groups by an inductive effect, because sp3 hybridized carbons are less electronegative than sp2 hybridized carbons, and so the more of these you have, the more electron density you can donate into the ring. But notice it's not as good as the amino, or it's not as good as the resonance, as the donors by resonance, not as good as amino or methoxy. Similarly, if you want to see, methyl is only just about the same as the T-butyl group. Interestingly, and this is something that I've had students ask about in undergrad OChem, if you take that amino group and acetylate it, the sigma value is 0, which means that the acetylated amino group has exactly the same equilibrium constant as the hydrogen does. Why that huge difference between an amino group and an acetylated amino group? What do you think's going on there?
Would it be that the lone pair of nitrogen is conjugated with the carbonyl?
Yeah, it's conjugated with the carbonyl, which should delocalize it this way and make it less able to donate into the benzene ring. Incidentally, we teach in the undergraduate textbook that anilines are way too reactive in bromination reactions. But if you want to attenuate their reactivity, you can just put an acetyl group on there. Okay, so these are all the electron donating groups. Now, as we tip over into electron withdrawing groups, what do you expect? How do you expect this sigma value to change? If we had an electron withdrawing group here, what would that do to our equilibrium constant? Just make it better, right? Bigger at least than the hydrogen, which is sort of our neutral point. So an example would be nitro. So why would you expect nitro to do anything? Well, just as with the methoxy group, you can draw a resonant structure for nitro where you pull electron density out of the ring. With methoxy where you put electron density in the ring. So with electron withdrawing groups, especially by resonance, you can put positive charge into the ring next to the carboxylic acid, and that stabilizes the conjugate base of our acid and makes Kx larger, makes our equilibrium constant larger. So let's just write some of the usual suspects of electron withdrawing groups. A ketone has a sigma value of 0.47. Okay, so that means that the equilibrium constant for having the ketone there versus having the proton there is some number between 1 and 10. And let's see, trifluoromethyl is another example. I think it's 0.53. This is an inductive electron withdrawing group. Nitro has the number 0.81. And actually, if you can have a quaternary ammonium where you can't donate via resonance and therefore all you see is the electron withdrawing effect, via induction, you get quite a large sigma value. Okay? So that follows along with what we expect for electron donating versus withdrawing groups. But now we're going to try to see how that influences a reaction. Okay. Any questions so far? We can talk about the meta parameters as well, but before we do that, I just want to give you an example of
So,
Yeah.
I would expect that at that power position, I would have expected that the nitro would be more favorable since it's by resonance.
Right.
Than the
Yeah, the trimethyl ammonium. Yeah, I'm not sure why that is. That's a great question, and it probably has to do with the fact that you got a full formal charge on that, full positive charge on that trimethyl ammonium group, whereas the nitro group, even though it's a good electron withdrawing group, it is neutral overall. Yeah, okay. So what we're going to do is we're going to run a related reaction and measure the rate or equilibrium constant for a reaction with a substituent versus hydrogen. And then we're going to plot that number versus this sigma value. So let's imagine that instead of benzoic acid, so instead of our reference reaction, we now have a test reaction. And suppose instead of benzoic acid, we do this reaction with the corresponding phenyl acetic acid. So we're going to move one carbon away. All right, and then we're going to measure the equilibrium constant for making the following conjugate base and hydronium. And then for all of these values, we're going to measure our own log of the equilibrium constant or reaction rate, whichever you want to do, versus the corresponding equilibrium constant when X equals hydrogen. And then we're going to plot the log Kx over Kh that we measure from our test reaction versus the sigma value that we got from the benzoic acid reaction. Okay? So let's just show you how this would work. Okay? For the benzoic acid reaction, if you plot log Kx for the substituent over Kh, and then here you have the parameter sigma, which we got from the benzoic acid reaction. That number, the slope of that has to be 1, right? Because that's how we got the sigma reaction, or that's how we got the sigma values. So I'm not going to worry about where the intercept is or what the units on the axis are. But for our reference reaction, which is the benzoic acid reaction, the slope here equals 1. Now, if you do the same reaction for our phenyl acetic acid, and you measure this log K for the substituent versus Kx, what you see is a slope that's greater than 0 but less than 1. All right, let's talk about what that might tell you. And let me ask you a question. And let's remember that we're going to have sigma values that go from negative to positive, and in the middle is going to be sort of 0, which is where hydrogen is. Okay? Is the phenyl acetic acid deprotonation more or less sensitive to the Hammett parameter than the benzoic acid reaction? And remember, the Hammett parameter describes just how electron donating versus withdrawing a group is. So relative to the benzoic acid reaction, is the phenylacetic acid reaction more or less sensitive? Less, right? Because as you change the Hammett parameter, the value of this equilibrium constant difference doesn't change as much. Okay, is that consistent with what we expect? It's less sensitive to the sigma parameter. Can you explain to me why that might be the case? Any thoughts? And if it's useful, I'll draw the conjugate base of benzoic acid. Why should it matter less for the phenylacetic acid what the substituent is here? Yeah, Heather.
Your ketone area is further away from the benzene ring, so the changes in the benzene ring affect it less.
Good, good. Your carboxylic acid is further away from the benzene ring, so you would expect changes in the benzene ring to affect it less. Recall for the I didn't really want to do that. Recall for the electron donating groups, we said the whole problem was that you could draw a resonant structure in which you donated extra electron density to the ring, and then you could put that directly by the carboxylic acid. And that was the case for the benzoic acid. And here it's still there, but it's not as close. Okay? So we could interpret the fact that the slope is not the same, is less than the slope for the benzoic acid reaction, as evidence that, like we expect, this reaction is less sensitive to the nature of the donating group, and that makes sense structurally. Now, so the magnitude of the slope is going to matter, the sign of the slope matters, right? Because in this reaction, we're still building up negative charge as we go from starting materials to products. So there are two things we can get out of this kind of analysis. You're going to look at the sign of the slope, which is going to tell you, is there a buildup of negative charge like with benzoic acid? Or is it going to be opposite benzoic acid and have a buildup of positive charge? So that's the first thing. And then the second thing, you're going to look at the magnitude of the slope. Is your reaction more or less sensitive to substituents as the benzoic acid? So what people do then is, for their test reaction, they will plot log of Kx over Kh versus the sigma parameter, and then they're going to fit those data to a line, and the line will have slope and the line will have some slope and some intercept. The slope we're going to call rho, because why not? Greek letters, right? Rho times sigma para, and then there will be some intercept, which I'm not going to even give a number to. All right? So this rho value is going to tell you things about the reaction. Is the reaction involving a buildup of negative charge or positive charge? And is the reaction sensitive? How sensitive is that reaction to the buildup of negative versus positive charge? So let me show you an example of a reaction that you would expect to be sensitive, but to the buildup of positive charge. before we go on, anything you want to ask about that? All right, so let's take some substituent there. Let's put a phenyl group here, a hydrogen there, and a chloride there. And we're going to measure the rate. Should we measure rate? Probably. Measure the rate of going from the starting material to product. Oops. And let's say we're using ethanol as our nucleophile. So this is a substitution reaction, right? So let's talk mechanism. And this is how you answer. Next time somebody asks you, how do I know that it's Sn1 versus Sn2? You tell them that they have to do an extensive Hammett analysis and plot rates of reaction for various substituents versus the sigma values, and then compare the slopes and see. There are two possible mechanisms here, among others, I guess, that we could expect. There would be the Sn1 mechanism, where your transition state would involve leaving of the chloro group and buildup of positive charge on the carbon that chloro was bonded to, versus the Sn2 mechanism, in which the rate determining step is, I did it again. The nucleophile comes in as the leaving group is leaving. Oh, why do I want to do Lg for leaving group? Chloro is not Gl. Okay, come on. Cl, and it's actually just a partial negative charge, partial negative on the nucleophile, not a lot of partial positive charge on the carbon, right? Because the nucleophile is coming in as the leaving group's leaving. So those are your two transition states, and the difference is how much positive charge is built up here versus here. All right, here, not a lot of positive charge. Here, lots of positive charge in the transition state. Okay, so let's think through these two major points. The sign of the slope for the Sn1 reaction. Remember, for the benzoic acid reaction, the slope is positive, and that's where electron donating groups make the reaction less favorable. What do you predict here? Does electron donating group make the reaction more or less favorable? For the Sn1 reaction, yeah.
Could you repeat that?
For the Sn1 reaction, if you have an electron donating group here, do you expect that to make the reaction faster or slower? Slower? Faster? Think through it. You got a positive charge build up adjacent to the benzene ring in the transition state. So you want a donating group to make it, because that's going to stabilize that transition state and make the reaction faster, right? That's opposite what the benzoic acid case was. Remember, in benzoic acid, you have a buildup of negative charge, so electron donating groups are unfavorable, destabilizing. So we're going to expect opposite dependence on the sigma parameter relative to benzoic acid. Or in other words, we're going to expect a slope, a rho value slope, that is less than 0. We're going to expect to get a negative rho value. If we plotted it up here, we would see a slope that went like that, because the reaction's faster for electron donating groups and slower for electron withdrawing groups. Okay. Now let's talk about magnitude for Sn1 versus Sn2. In the Sn1 reaction, there's a bigger buildup of positive charge than in the Sn2 reaction. So what do you expect the magnitude of the slope to be? Bigger slope, more negative slope for Sn1, or lower dang it,
The
size of
slope
negative
the
numbers.
Sn1 should be like more steep.
Okay, good. Steep is a good word. Thank you, Heather. Steeper slope for Sn1 versus less steep slope or shallower slope or something for the Sn2 reaction. Okay? And so you could determine which of these mechanisms was more consistent with the data. And I wish I had an actual number to tell you. My guts say the Sn1 mechanism describes it better. All right? But you can actually, people will do these experiments to provide evidence for against reaction mechanisms. So next time you're in the tutorial lab helping somebody, help them by telling them all of this and see what happens.
They will blink in a confused.
They will blink and then they will run. It's a win-win for everybody.